Good evening. Today I want us to look at another topic called linear programming. Linear comes from the term line. So what is linear programming? Linear programming, that is in short form LP, is a mathematical technique that deals with the optimization. When I talk of optimization, you will either maximize or minimize linear functions of variables known as objective function. Remember, in a business, our aim is either to maximize our profit or minimize our cost. So our profit and our cost are going to be our objective function, which must be subject to a set of linear inequalities known as constraints. For us to achieve the objective function, there must be some well-defined constraints. The objective function may be profit or cost, which is to be obtained in an optimal manner. The constraints may be imposed by different resources such as labor, the labor available, the finance that you have, materials available, the machines, and technology. So a linear programming problem, that is LPP, linear programming problem, has two basic parts. The first part is the objective function, which describes the primary purpose of formulation. It is either you maximize some profits or you minimize some cost. The second part is the constraint part, which is a system of inequalities. Remember, inequalities, just taking this, I can take those signs. Yeah, we only have these four symbols of inequalities, but equation is only equal, the equal sign. So these concepts, they just set of inequalities describing the restriction under which optimization is to be accomplished. What are some of the conditions for linear programming problem? Conditions for linear programming problem. The first condition is there must be a well-defined objective function, which is either to be maximized or minimized, and which must be expressed as linear functions of decision variables. There must be restrictions on the amount of extent of attainment of the objective, and these restrictions must be capable of being expressed as linear inequalities in terms of variables. And number three, there must be alternative course of action. There must be alternative course of action. That simply means that that product must be produced by two machines. There must be two machines in production. And then the decision variables should be interrelated and non-negative. They should not take any negative value, because remember, you are producing, so when you are producing a list, you have to produce something. And the resources must be limited in supply. We have the assumptions of linear programming problem. The linearity, we assume that these decision variables are linearly correlated. Certainty, you know in advance the parameters which are used, and they are constant, they don't change. Non-negativity, these decision variables only assumes the positive values. We don't accept the negative values. Then divisibility, if you get any answer which is a fraction or a decimal, that answer is valid. So let's look at some of the methods you can use to solve some linear programming. Actually, for now I have these two methods. Other methods will be done in managerial accounting. But now let's look at the graphical method and simplex method. So in the graphical method, these are the steps you are going to follow. Step number one, you must know how you can formulate the appropriate linear programming problem. Formulation first. Then we are going to graph the constraints. Don't graph the objective function, but graph the constraint inequalities as follows. Treat each inequality as though it were an equality, and each equation arbitrarily select two sets of points. I'll show you that when I'll be taking an example. Plot each set of points and connect them with appropriate line. When I mean appropriate line, when you use an inequality of less or equal to, then I'm expecting a full line. But when I use less, then you have to use dotted line, appropriate line. Identify the solution space or the feasible region which satisfies all the constraints simultaneously. Remember, you will check the area that you don't want and you will be left with the area that you want. So that area that you want is what we call the feasible region. Then locate the solution points on the feasible region. And these points always occur at the corner points of the feasible region. So these are the points that we are going to use to evaluate our objective function. Now the fifth step, you have to evaluate the objective function at each of the corner points. So you will have to evaluate the objective function at each of the corner points. Then identify the optimum value of the objective function. Now I have a note below here which is very important. Suppose you are doing a minimization problem, that is, you minimize cost, the constraint will be of greater or equal to. And when you are doing maximization problem, then the inequality we are going to use is less or equal to. Let's take this example here, example 1. I have example 1. Alpha Manufacturers produces two products P and Q, whose contribution per unit is Kenya shillings 60 and Kenya shillings 40 respectively. The resource requirements for each product are as follows. So we have resource, product is either product P or product Q, and what is available. This is what is available. The skilled labor, hours is 1 hour in P, 2 hours in Q, and what is available is 6,000 hours. And skilled labor 2 hours, 3 hours, what is available 9 hours, and materials in kg, 4 hours available for P, and 1 kg available for that Q. What is there is 2,000. Roman 1, you are asked to formulate a linear programming problem. And Roman 2, using the graphical method, determine the optimal product mix, and that will earn you 10 marks. Now, I've started by saying, let X be the number of units of product P produced. And also let Y be the number of units of product Q produced. So these X and Y are my decision variables. X and Y are my decision variables. So what is my objective function? Is to maximize, because remember they are producing, after producing, they are going to sell. What their contribution is here. So when they sell, P is being sold at 60 and Q is 40 more. So they are maximizing profit Z, which is 60X plus 40Y. For this one to be met, there is constant part subject to. Now the constant part is coming from the resource. 1 times X is just X plus 2Y is less or equal to 6,000. I've used this inequality because it is a maximization problem. And skill, you have 2X plus 3Y less or equal to 9,000. And in material, you have 4X plus Y less or equal to 2,000. And remember, we talk of non-negativity, that decision variables only assume the positive value. So X and Y must be greater or equal to 0. So that is step number 1. I've formulated the appropriate LPP. Now I'm going to graph it. We are told that for you to graph, then treat each inequality as though it were equality. This is what it means. Block this and say X is equal to 6,000. So X is 6,000. When you block X, you say 2Y is 6,000. What is Y? it will be 3,000. So the two sets of point is 6,000 for x and 3,000 for y. Do the same to this. If you block this, x will be 4,500 and y will be 3,000. I've just broken, that is what I've obtained, what I'm going to plot. Then come up with your graph paper. Please do this one in a graph paper. I'll just use this for illustration, but please plot this in a graph paper. So draw your Cartesian plane. Choose a very nice scale that will accommodate your values. So I've tried to reduce mine. So the first constant is 6,000 and 3,000. 6,000 is here, 3,000 there. Join using a continuous line and always shade the upper part for maximization problem. So you shade that area, you don't want that area. This one 45 and 3,000, 45 is here, 3,000 is there. You will shade, just join and shade the upper part on the left, and 500 and 2,000, 500 and 2,000 is here. I shade. So I'm remaining with a small piece. This is the feasible region you are looking for. This is the region you are looking for, the one I've marked with R. The one I've marked with R. So remember step number 4, we are told to identify the corner point. So this is the first corner, the second, and the third. The first one are given it A, the second B, and the third C. So at A, the coordinate at A is 0, 0. That means no production has taken place. At B, the coordinate is 0, 2,000. This simply means 0 units of P is produced and 2,000 units of Q is produced. This one is yielding what? Remember, I'm trying to calculate the profit here. 60x plus 40y. So at 0, 0, there will be no profit made here because no production. Here, 60 times 0 plus 40 times 2,000, the profit made there is 80,000. And at C, with a coordinate of 500, 0, then this one is yielding a profit of 30,000. So what is the maximum between this 0, 80 and 30? 80 is maximum. So maximum profit is 80,000. Thus, 0 units of P and 2,000 units of Q should be produced in order to maximize profit. And that is how you can use graphical method to solve linear programming problem. So tomorrow I will take an example dealing with minimization problem. This is maximization problem. Let's meet tomorrow in our next class to discuss the minimization problem, and that will be the end of linear programming as a topic. Draw our second example under linear programming. And this one I've taken an example about cost minimization. Let's read the example. The following is a formulated linear programming problem. This is linear programming problem relating to two components, 1 and 2, purchased by the Tambo Limited. Let the number of units purchased of component 1 be X, and also let the number of units purchased of component 2 be Y. And we are told the objective function is to minimize cost. The cost is denoted by C, which is 40x plus 20y, and this is subject to the first constraint is 2x plus 4y greater or equal to 80. You can see, due to minimization problem, they have used greater or equal to. The second constant is 6x plus 2y greater or equal to 60, 8x plus 6y greater or equal to 120. And due to non-negativity, x and y must be greater or equal to 0. So we are being asked that using the graphical method, determine the number of units to be purchased of each component and the minimum total cost. Now, remember we are going to graph the constraints, and I say you need to look for the coordinates you are going to plot. So I've started by the first constraint. I've blocked the 4y and said 2x is equal to 80. What will be x? You will find x is 40. Then block 2x and say 4y is equal to 80. What is y? 20. So the first coordinate, I've gotten 40 and 20. Do the same to the remaining two. Just block 2y and say 6x is 60 and x will be 10. Then 2y is 60 and that x will be that 10. This one the same. 8x is equal to 120 and your x is 15. 6y is equal to 120 and your y is 20. So when you go to your graph, don't have a graph, so when you draw this in a graph, you will find exactly the values. First constraint, remember the x is 40, you can see I've marked 40 here, and y is 20, and I've marked 20. Then join using a full line, But since it is cost minimization, it is the downer part that we don't want. So I've shaded the downer part which we don't want. The second constraint is 6x plus 2y greater or equal to 60. Remember, x is 10. This is where I marked 10. And my y is 30. Y is 30 here. Join those 2 points using a full line. Then you shade the downer part. And the last constant is 8x plus 6y is 120. So there we have the coordinates of 15. 15 is here. And 20. Here. Then join using a full line and you shade the downer part. So which part, where is our feasible region? Our feasible region is here. That is the region that we want. This is the region that we want. The all of this upper part is the region that satisfies all our constraints simultaneously. Now let's try to find the corner points. The first corner is here. I've marked it, let it be A. This is the second one, let it be B. And this is the third one. I've marked it C. So at A, the coordinate is 40,0. This is 40,0. At B, I don't have a graph, so I've just estimated, but once you draw it, you'll find exactly values in your graph. So I've just estimated to be 6,19. By looking at my graph, I've just estimated it to be 6,19. And at C, it is 0,30. Then I've tried to evaluate the objective function at each of the corner points. So at A, you remember objective function is 40x plus 20y. So x is 40. 40 times 40 plus 20 times 0 will give me 1600. At B, 6 times 40 plus 20 times 19 will give me 620. And at C, 0 times 40 plus 20 times 30 will give me 600. So if you look at this cost here, the minimum cost is 600. So if they buy 0 components of 1 and 30 units of component 2, their cost is minimum. So to answer Roman 1, they should purchase 0 units of component 1 and 30 units of component 2 in order to minimize their cost. And the minimum cost is 600 shillings. Try draw this in your graph and you will exactly find the correct value for the point B. I've just estimated it using my graph. That is our example 2, and that will be mark the end of our linear programming as a topic. The simplex method is when maybe we have more than 3 components and it is involving, but I want us to concentrate on this graphical method. Let's concentrate on the graphical method because it looks more easier. It looks more easier, you can handle. But remember, you can only use this when the number of components or product produced by a company is 2 or less. Let's meet in our next topic, which is probability. Welcome.